All right, so let's talk about graphing some stuff. This equation, x squared plus y squared plus z squared equal to 36 is going to give us a sphere. And you can recognize that from having x squared plus y squared plus z squared, right? When you ever see those things together, it's kind of just like how x squared plus y squared equal to 36, for example, is a circle. If you add another dimension, we're just adding another dimension. So this is definitely a sphere. It's centered at the origin. And the radius is 6. It really is coming from the distance formula, right? I mean, you could say that, right? If you really, really wanted to, just to kind of talk more about this, well, let's graph it. The graphing part is kind of not the hard part. Here, I'm really just going to kind of eyeball it and say, okay, well, I'm going to try and draw like my circle in the plane here. And then my other kind of circle like this. Like that. There's my, I feel like I meant, oh, yeah, you got there. There's my sphere of radius 6, and you could label some points if you wanted to, but I don't think we really need to. But the thing that's true about the sphere is that any point on the sphere, x comma y comma z, the distance from that point to the center should be a distance of 6. So just to give ourselves a little more analysis here, you could say, oh, well, the distance formula, which is the square root of the difference in the x's squared plus the difference in the y's squared plus the difference in the z's squared, that should equal 6. So that's really where that equation is coming from. Because then you square both sides and you just get x squared plus y squared plus z squared equal to 6 squared. Again, not super important to know exactly where this comes from, but it seems worthwhile to mention. So let's do a couple more examples of spheres. In this next one, the question is to find the center and radius of the sphere given by this equation. X squared plus y squared plus z squared, 8x minus 6y plus 2z plus 16 equal to 0. And we know it's a sphere because we see x squared plus y squared plus z squared. That's usually the indication. Or really, I should say, if x squared and y squared and z squared are all the same sign and have all the same coefficient. So it could be like 3x squared plus 3y squared plus 3z squared equals some other stuff. That would also be a sphere. So the problem is, if we want to find the center and the radius of the sphere, we have to write this in the kind of standard way, where we do the completing of the square. So we're going to write this as x squared plus 8x plus, and we're going to leave ourselves a little bit of room to complete the square. And we're going to have y squared minus 6y. We're going to leave ourselves a little bit of room to complete the square. And we're going to have z squared plus 2z plus, again, a little bit of room. And I'm going to bring that 16 over to the other side and make it a negative 16. And then I know that if I add stuff on the left, I'm also going to have to add the same stuff on the right. All right, so to complete the square, we take the coefficient of x, we divide it by 2, and we square it. So 8 over 2 is 4, 4 squared is 16. Add 16 there, I got to add it over here. And same deal for the y's. Y squared minus 6y, the negative 6 needs to get divided by 2 and then squared. So that's going to give us a plus 9. We add it over here as well. And then the z squared plus 2z, I need to take that z divided by 2. Sorry, take that 2 and divide it by 2. Square it. I'm going to add a 1. And the whole point of completing the square is now each of these things with the x's or the y's or the z's can be written as some quantity squared. So this first part's going to be x plus 4 squared. The second part's going to be y minus 3 squared. This third part's going to be z plus 1 squared. The nice thing about writing it this way is you can kind of see that when this 8 over 2 is the 4 that goes right there. This negative 6 over 2 is the negative 3 that goes right there. This 2 over 2 is the 1 that goes right there. And it's equal to These 16s cancel, we get 10. So the center is going to just, and really it's just like a circle, right? It's just like a circle, you're just adding another dimension. So the center is the XYZ coordinate that makes the entire left-hand side equal to 0. So that's going to be X equal to -4, Y equal to +3, and Z equal to -1. And the radius is going to be the square root of this number over on the right-hand side. So we're going to get R equal to the square root of 10. Just like over here, the radius was equal to the square root of 36, which was 6. Cool. Spheres, kind of interesting. They come up relatively frequently, so they're worth mentioning. Let's go ahead and.
Is that how you complete the square every time?
Yeah. Yeah. So the thing to remember about completing the square is you want to keep all your different variables separate, right? So the X's should be one piece, the Y should be another piece, the Z should be another piece, and we have to complete the square for each of them. Yeah. And some people like to do the thing where like they add 16 here and subtract 16. I'd feel like if I've got two sides of an equation, I might as well add 16 here and add 16 here, and add 9 here and add 9 here, and add 1 here, add 1 here. I mean, it makes sense. Yeah, but that's pretty much the same thing every time. All right, let's talk a little bit about functions of two variables and domain and maybe range. So just a quick reminder, recall from before, if you had a function like f of x equal to the square root of x minus 3, the domain is the set of all x values, or I like to think of as inputs, right? Things that we can put into the function that can be input into f of x and give a real output. It does need to be real. I will point out, even though we don't use this language often, whenever we talk about functions in the context of calculus, we are always talking about what are called real valued functions, where the outputs have real values, as opposed to imaginary numbers, right? We don't typically talk about functions where the outputs are imaginary, although that's something that can be explored in other classes. We're not doing that. So that's why here our domain would be, well, we can't take square roots of negative numbers, so we need x minus 3 to be greater than or equal to 0, which translates to x being greater than or equal to 3. So our domain is the set containing everything from, sorry, not that way, everything from 3 to infinity. That'll be our domain, written in interval notation. And graphically, if we drew this function, it's just your usual square root function shifted 3 to the right. So it looks like this. And we can see that the domain is just the portion of the x-axis where the function is defined. So all this stuff here, right, that's our domain, where x is bigger than or equal to 3. And since we're at it, we might as well note that that also allows us to see what the range is if we're able to graph it, right? The range is just all the corresponding y values. So all of this would be the range, which is specifically y being greater than or equal to 0. The domain here is everything from 3 and larger, and the range is everything 0 and larger. So if we wanted to, and what I do want to, the range we could write down is going to be everything from 0 to infinity. Great.
Someone's already given up on their confidence for the midterm.
Oh no, what happened?
There was someone sent a message to the Discord asking, does he curve?
Oh, well, sure. I mean, that's always a fair question, but yeah, it definitely is indicative of someone's like, I don't feel great about that. Hopefully there's a curve. So what I think most teachers do, if there's going to be some sort of curve, is they usually kind of wait till the end of the quarter and calculate your final grade and then maybe curve that in some way. But curving the individual exams doesn't, I don't know, it probably makes students feel better, but it doesn't really, like, it's not the whole picture, I feel like. So curve or not, I don't think that's something that people really actually do, with some weird exceptions. Maybe like last quarter, there might have been some weird exceptions. until the end of the quarter. So that's the grain of salt I would take with it. So let's now look at a function of two variables. Let's see, sure. So let's say we've got this example. F of x comma y is, sure, let's say it's the square root of 9 minus x squared minus y squared. A couple things to point out. Next, I'm gonna go back to the previous page for just 1 second here. So here the function was f of x squared of x minus 3. And I just want to point out, when we think about this, we often think about this as y equal to the square root of x minus 3. Or in other words, we often use the typical substitution or change that y is equal to f of x. Right? That's usually our thought process. Y, f of x, same sort of deal. In the same sort of way, when we're talking about f of x, y equals the square root of 9 minus x squared minus y squared, we're typically thinking of this as like z equal to the square root of 9 minus x squared minus y squared, because we are thinking of z equal to your function of x and y, just like y is equal to your function of x. So the reason I mention this is because if we look at it that way for just a second, we can kind of see what shape this has. This function, if we square both sides, z squared equal to 9 minus x squared minus y squared, and then if we bring all the variables to the left, that's going to be what kind of shape? X squared plus y squared plus z squared equal to 9. Right. But, so you're totally right. This would be a sphere. But if we go back to the original equation up here, well, in that original equation, z can't be negative. Because whenever we take a square root, we only get positive results. So this would be the top half of the sphere, where z is positive and x and y can be whatever. So here's what this looks like. And I'll do my best to graph it here. Yeah, kind of like that. So I've got a sphere of what radius? Yeah. So the top half of the sphere radius 3. Do our best to draw it here. Cool. That looks all right. And so this would be the point, well, this would be the point like 3, 0, 0. This would be the point 0, 3, 0, 0, 0, 3. Not that we need to label all these, but it's kind of just nice to see what they are. So here's what I want to point out. My domain here is all of this inside of the circle in the XY plane. That's my domain. It's all the things that X and Y are allowed to be at the same time. So all the ordered pairs, X comma Y, that makes sense. So to be super explicit about it, I'll just point out that, for example, the point 4 comma 4 is not in the domain. Right? If you plug in 4 comma 4 for X and Y, you're going to get the square root of something negative. Doesn't work. The domain here, however, we have to describe not as just some interval, right? Because it's not some length on the x-axis, it's some area in the xy plane. So here what we're going to say the domain is, and so what we're still going to do is we're still going to use the same sort of rules for domain that we would have previously for functions of one variable. We still can't take the square root of a negative. We still can't divide by 0, and we still can't take the logarithm of 0 or negative. So the same rules apply. It's just now the input is more complicated. So just like before, we're going to say that the stuff we're taking the square root of has to be non-negative. Now, something that happens often with functions of two variables is you see an x squared plus y squared. It's usually a good sign. It usually means things are going to be not too terrible. So I would definitely think of this as 9 minus the quantity x squared plus y squared bigger than or equal to 0. And then I would bring the x squared plus y squared over to the other side. So I have 9 bigger than or equal to positive x squared plus y squared, or just to change the order so it looks more like something I'm used to seeing, x squared plus y squared less than or equal to 9. Which is exactly all of the xy values that are inside the circle of radius 3. So what I usually do when I see an equation like this, or not an equation, actually an inequality like this, is I think about the equality. So I say, okay, well, I know that x squared plus y squared equal to 9 is the circle of radius 3, centered at the origin. So then I just have to ask myself, are the points I want inside the circle of radius 3 or outside of the circle of radius 3? Because typically what happens is the equality gives you a boundary, and then you're always on one side of the boundary. You're either always inside or always outside. Or if your boundary is like a line, you're either above the line or below the line. So once you pick a point and see if it's either part of the domain or not, everything that's on the same side as that point is also in the same being in the domain or not being in the domain. So for example, the point 0, 0 is for sure in the domain because it satisfies the inequality. 9 minus 0 squared minus 0 squared is for sure bigger than or equal to 0. And since 0, 0 is in the center of the circle, everything else inside the circle is also in the domain. Now, writing the domain is kind of a pain. I would probably just use words, to be honest. So in this case, I would say the domain is all the points inside the circle of radius 3. But if you want to be a little bit more mathy about it, the way we usually write the domain is using set notation. It's going to be the set containing all points x comma y such that x squared plus y squared is less than or equal to 9. It's kind of almost not really any work. You take your condition, you maybe simplify it to look a little bit nicer, but then you just say, okay, I want all the xy points that do the thing that needs to be done to meet the domain requirements. Kind of it. We could also talk about range here. The range here is pretty easy to see graphically because we graphed it. What's the lowest z value we get? What's the highest z value we get? And the way I think about that a lot of the time is by writing this function, especially if you see an x squared plus y squared, as in this case, 9 minus the quantity x squared plus y squared. And the reason we do that is because we know that x squared plus y squared specifically is always greater than or equal to 0. Has to be. X squared plus y squared, x squared is non-negative, y squared is non-negative, their sum is non-negative. So the smallest that can be is 0, which means the biggest this whole thing can be is the square root of 9 minus 0, which is 3. And then the biggest x squared plus y squared can be, if we think about the domain, is 9. So then the smallest this can be is 9 minus 9, which is 0, and the square root of 0 is 0. And that's why we're getting 0 to 3 as our range. So the range, I'll just write right here, is still written in the usual kind of interval notation. We're getting everything from bracket 0 to bracket 3. Range can be dicey. It's not always going to be super easy to be like, oh, I can see how big this function gets and how small this function gets by just doing some brief analysis. But it's something that we can kind of still do. And most of the time, people aren't going to care too much about asking about range, but your teacher might. So we'll look for that. I'll look for that in the next homework assignment whenever it gets posted. Questions so far? Okay, let's look at a few more examples. Sure. Yeah. So let's say we've got this function here. That's a good one. F of x comma y is equal to the square root of, I'm going to change it just slightly. Yeah. Let's make it x minus y over x minus 2. And we're going to find the domain. Okay, so I see two pitfalls here. One is that there is potentially division by 0, and 2 is that there is a square root. So we have to deal with both of those. I think the bottom one's pretty easy to deal with. If we have x minus 2, well, I should say we want to exclude x minus 2 equal to 0. That means x equal to 2 is what we're excluding. So if I start, and I'm going to find the domain, I should have find the domain and graph it. What is interesting? Sounds very loud. The reason we say graph it is because usually graphing the domain is the easiest way to actually have an idea of what it looks like. So here's my XY plane. And I know I need to exclude x equal to 2. So if you want to exclude something, typically draw it with a dashed line. So I'm going to go over to 2, and I want to exclude everything on that line. So I draw it that way. Great. And then we also have the requirement that the stuff inside the square root, x minus y, had better be bigger than or equal to 0. So if I can, if I'm trying to find like a requirement here, if I can solve for y, that's great because I know how to graph y as a function of x typically. So here, if I solve for y, I could say I've got, I could either, I would go this way, x less than, or sorry, x bigger than or equal to y. But if you prefer, you could have left the negative y on the left and subtracted x from the right, and then multiply both sides by -1 to get y less than or equal to x. Either way, you're getting the same thing. I just like writing it like this because it just looks more like we're used to seeing it because y is on the left. So I'm going to graph y equal to x. And now since I do want to include the line y equal to x, I'm going to draw it solid as opposed to dashed. So here's my y equal to x. It is part of the domain. It's totally fine for y to equal x unless they're both 2. That'd be a problem. But if like y and x are both 3, that's totally in the domain. So for example, the point 1, 1, totally in the domain. The point 3, 3, totally in the domain. Any point on this line is in the domain except for the point 2, 2. I might draw a little open hole here. Just make sure it's extra clear that that's not in there. So now, this border that came from this inequality being an equality, right? We graphed y equal to x. This border separates the domain from the not domain. So either this side is the domain and this side isn't, or vice versa. This side's the domain and this side isn't. And the way we tell is by checking any point on either side. So pick an easy point. Well, except don't pick that point. Don't pick 2, 0. Pick something like 3, 0. So does 3, 0 satisfy the inequality? Yeah, it does, right? If we plug in 3 for x and 0 for y, that works. So that means this point and every point on this side of the border is in the domain. So all of this is in the domain. And none of this is. If we tested a point over here, like, I don't know, 0, 3, it would not have worked. X being 0 and y being 3 doesn't satisfy the inequality. So you only ever have to test one point, really. And then if it works, great, everything on that side. If it doesn't work, great, everything on the other side. If this sort of question were to come up on web work, what they usually do is they say, find the domain, and then they give you like a drop-down list of like 10 options of how to describe the domain. So this domain would be described as a half of the plane, because you're getting this entire half of the plane with a line excluded. So you're getting all of this half of the plane except for where x is equal to 2. Kind of funky. Let's look at one more example. Let's look. So usually you're not going to ask about range here. But if someone were to ask about range, here is what I would say. And this question, you really can't do anything other than try and think about how big this could be and how small this could be. So look, here's my domain. I can pick any points out here. I'm going to try and make my life a little bit easier by first picking an x value. If I pick x equal to 3, then my function now becomes f of 3 comma y. I'm plugging in 3 for x, and I get the square root of 3 minus y over 3 minus 2. I picked 3 specifically because I knew it was going to make my denominator equal to 1, which really means I really just got the square root of 3 minus y. Now, I'm on this line, right? I'm on this line here where x is equal to 3. And y can be anything that's less than 3. And if y gets more and more and more negative, this square root can be as positive as you want it to be, right? If y was negative a billion, this would be the square root of 3 plus a billion, which is a large number. It's not that big, right? But right, like as you let y get more and more and more negative, this goes to as positive as you want it to be. So we can certainly see that, okay, if x is 3, the z values can be any number greater than or equal to 0. And then similarly, if we pick x equal to, say, 1, then we get f of 1 comma y equal to the square root of 1 minus y over 1 minus 2, which is negative 1, which is just the negative square root of 1 minus y. And in a similar way, if we let y range from 1 to negative a bajillion, you can get any negative number you want. So this is going to give us all the z values that are less than or equal to 0. And this shows me that z can be any positive number, z can be any negative number. So here the range is everything, which often happens. There are other more algorithmic ways of doing this. Like you could set this equal to some constant c and then try and solve for x or y in a way that makes it so you can be like, well, c can really be anything. But it's, I don't know. I wouldn't worry too much about it, which is why I'm trying not to talk too much about it, but doing a bad job of it. So yeah, okay. Let's look at one more example. Let's say we have f of x comma y equal to the square root of, let's go 9 minus x squared plus the natural log of 4 minus y squared. So again, we've got some usual suspects as far as domain goes. And we're going to both graph and express the domain. As a set. I suppose I didn't do it for the last one. So if you wanted to write the last domain as a set, it's kind of annoying, right? You just have to be like, okay, the domain, just to point out, you could write as the set containing all points x comma y, and then you just have to basically write down all the conditions that need to be met. So we have to have that y is less than or equal to x, and x is not equal to 2. That's the annoying way you would write the domain. But there's not really much to it, right? You're just taking the things you already know have to be true and writing them in this set notation. Okay. Back to this other example. Right. So here we've got two conditions we need to meet. We need for both 9 minus x squared to be bigger than or equal to 0, and 4 minus y squared to be strictly bigger than 0. All right, that's not too terrible. So here, you can do this any way you want. I think we've probably got enough experience now to be like, we know that if we write this as 9 bigger than or equal to x squared, or if you prefer x squared less than or equal to 9, that you're going to get x being between positive 3 and negative 3. If x is too negative, x squared will be too big. And if x is too positive, x squared will be too big. Or you could do the more work where you do like the factoring and stuff. But I feel like we can go from here to here without too much trouble. Similarly, we're going to get 4 bigger than y squared, or y squared less than 4, which means y is going to be between 2 and negative 2. Okay, so for the x's, we're going to include the boundaries because we want x to be able to equal 3. For the y's, we're going to exclude the boundaries because we don't want y to equal 2. So if I draw this, X can go to 1, 2, 3, and -3, and Y to 1, 2. So I would draw this as a rectangle where I'm excluding the line Y equal to 2 and excluding the line Y equal to -2, but including, except for this point right here, including the line X equal to 3 and X equal to -3. I don't want the point 3 comma 2 or 3 comma -2 or -3 comma -2 or -3 comma +2, because those would have Y values equal to 2 and I can't take the natural log of 0. So here's my domain. And then if someone really, really wanted to, you could write the domain as the set containing all points X comma Y such that X is between -3 and 3 and Y is between -2 and 2. But it feels kind of silly because it feels like we've already almost done it. Okay. Let's see. What else do I want to say about this? Not a whole lot. Okay, so you said we haven't talked about trace or level curves, right? Okay. You talked about functions of two variables. Didn't talk about partial derivatives or anything yet. Okay. Okay, let's look at a. I'm trying to think about like where he's likely to go. No, I don't have a good intuition. But yeah, let's take a look. Maybe we'll take a look. Maybe we will. Really taking your time here, Google Chrome. All right. Someday we'll get there. Okay, let's see. Like syllabus is kind of hidden. Or at least not wherever. I thought like I was expected to be under the syllabus, but it's not like in files. There we go. Syllabus. Sure, syllabus again. Let's see here. So functions of several variables, partial derivatives. Okay, let's move on to partial derivatives. So partial derivatives. What are they? How do we find them? What do they mean? So let's look at an example. Let's look at the function f of x, y equal to 9 minus x squared minus y squared. And if I want to take a partial derivative here, the idea is that if you're taking a partial derivative with respect to a certain variable, you're essentially asking yourself, how is this function changing as only x changes and as y remains the same? Or, well, so actually, let me write that. Typically, the notation for this is either f sub x, which people just pronounce as fx, right? You don't say the sub part, you say fx, or del f del x. It's not a d, it's a little curvier. It kind of curls back as opposed to be straight up. It doesn't really matter. Like, it matters a little bit. No one's ever going to ding you for accidentally writing d instead of del or del instead of d, but just be aware that it is a curly looking thing. And the reason there's a difference is because you can't just take a full on derivative of a function of two variables, because you have to specify what function you're differentiating with respect to. So if you've got a function of more than one variable, we can only really take partial derivatives of that function. So this is asking or talking about is how f of x comma y is changing as we move in the x direction and hold y constant. And similarly, Fy, which we could write as del F del Y, is how the function is changing if we move in the y direction. And hold x constant. So let's actually look at what this thing looks like. And instead of trying to draw a not excellent picture for you, I'm just going to steal this picture over here that I already have drawn from Grant, because Grant's a better drawer than me. It's okay. Everyone's got different skills in life. Not everyone can be good drawers. So here is the picture of this shape. 9 minus x squared minus y squared is what's known as a paraboloid. It's like a three-dimensional parabola, right? It's just parabola, something kind of rotates around. And we're going to look specifically at the point 1, 2, 4, which is right here. We've gone out 1, over 2, up 4. So right about that. And so if I look at this, if I'm traveling now, and I should be specific here, when someone says we're traveling in the x direction, what they really mean is we're traveling in the positive x direction, right? Just like if I say, like, if we're looking at like a function of one variable, like y equals f of x, and I say, what's the derivative? We're asking, how is y changing as x is changing? But specifically, I mean, how is y changing as we move from left to right, meaning x is increasing. So unless someone's specific, whenever it says we're finding a partial derivative with respect to x or y, you're always saying, okay, how is my function changing as x is increasing? Or how is my function changing as y is increasing? That's always the implied assumption, unless they say something different. So here, let's just pull this up over here. If we move in the positive x direction, which is that way, are we traveling downward or upwards? We're traveling downwards, we're traveling kind of away from the middle. We're going down, down, down like that. So we would expect, since we're traveling in the downwards direction, our derivative to be negative at that point. Because our slope, right, our tangent line there definitely has a negative slope in the moving outward direction. Now, talking about negative slope or positive slope, it really is a matter of perspective, right? Because you could be like, well, if you look at this tangent line I've drawn from another direction, it looks like it's a positive slope, right? It's kind of weird, I know. But if you let me draw a picture, even though I said. So I'm going to look at that, but I'm specifically going to look at it from the XZ coordinate system. So we look at that, then here's my big, surface, this is my Z equal to 9 minus x squared minus y squared. And this is where I should have talked about trace a little bit. Because what I'm doing is I'm drawing the trace of this function in the XZ plane. In other words, I'm letting y be 0 so that I can just deal with the XZ plane. So now if I look at the point, what was my point? It was 1, 2, 4. So x was 1. Y is 0. Okay, fine. There are lots of different traces you can use. You could use y equals 0, which is the standard one, but what I really should have said, I actually want y to be okay. Fine, I'm gonna draw it again. So this is the trace where y equals 0, and then over here is the trace where y equals 2, which I'm going to get z equal to 9 minus x squared minus 2 squared, which is the parabola 9 minus 4 is 5 minus x squared. So if I draw this one instead, that's why I don't draw. That's 9, 5. So we get this kind of shorter parabola. Right. So what I'm really kind of talking about, back to this like 3D picture, is here's the big parabola I just drew mistakenly, where y is 0. And then here's the smaller parabola that I actually want to draw when y is equal to 2. But either way, this one or this one, we are holding y constant. Right, along this whole parabola, y is 0. Along this whole parabola, y is equal to 2. or more importantly, y isn't changing. Okay, so if I look over here at the point 1, 2, 4, I can see that the slope of the tangent line is indeed negative. Right? That has a negative slope, which is the whole point I wanted you to see. Right? If we look at it from the correct perspective, the slope is indeed negative. Okay, what is the slope of this tangent line? Well, we find the slope of a tangent line the way we normally would, by taking the derivative and plugging in the point. So if I take my function, f of x y equal to 9 minus x squared minus y squared, and I take the partial derivative, let me write this down again, just so we don't lose it later. We take the partial derivative with respect to x, meaning I'm asking, how is this function changing as x is increasing and y is being held constant? What's the derivative of 9? What's the derivative of negative x squared? And y being constant means the derivative of y squared is 0. So when you take a partial derivative with respect to one variable, every other variable gets treated like a constant. And that is the real crux of partial derivatives, is that when you differentiate with respect to x, you pretend like anything else, y, z, q, u, whatever else is in there, it's just a constant and its derivative is going to be 0. If it's by itself. If you have it multiplied by something else, then you have to use your other usual constant rules. So then if I wanted to actually find the derivative at that point, 1, 2, 4, I'm going to plug in the point 1, 2, 4. Specifically, I'm really just plugging in 1 for x, so there's nowhere to plug in 2 for y or 4 for z. So the slope at that point in the x direction is -2. And in a similar way, we look back at this picture over here. If instead we go in the y direction, right? So if we draw this little parabola that way instead, and ask what's the slope going to be in the y direction? Well, it's still going to be negative, but it's going to be different. So if we find del f del y, which is also, well, not also, which is going to be 0 minus 2y, then del f del y evaluated at that same point is going to be -2 times 2, which is -4. The real point here, though, isn't, so it's nice to have the graphical interpretation so you can see what these things really mean, right? If it's del f del x, you're just asking, how is the function changing if I move in the positive x direction? And if it's del f del y, you're asking, how is the function changing if I move in the positive y direction? But the bigger picture here, or the more important thing really, is to be able to correctly find partial derivatives by using the fact that we're thinking of the other variables as being constants. So, yeah, I don't think I want to double check. Yeah, I don't want to do all that yet. Yeah. So let's go ahead and do it this way. So let's look at a couple. Yeah, I got 1 minute. All right. So let me just show you one example real quick, and then I will leave you on your way. So in this next example, we have f of x comma y equal to x to the 4th plus y cubed plus x squared times y to the 5th. And if I want to find my partial with respect to x, which you could either write as del f del x or as fx. So every x is counting and every y is a constant. So the derivative of x to the 4th is 4x cubed. The derivative of y cubed, well, y cubed is purely constant, so derivative of y cubed is 0. And x squared times y to the 5th. So if you have a function times a constant, the constant hangs out, and you multiply it by the derivative of your function. So we're going to get 2x times y to the 5th. It's very similar to how, like, for example, if you take the derivative of sine of x plus 3, well, the derivative of sine of x is cosine x, and the derivative of 3 is 0. But if you take the derivative of 3 times sine of x, you get 3 times cosine of x. Because constant multiples hang out. whereas constants on their own have a derivative that's 0. And then to finish this off, if I want to find del f del y, which is fy, the derivative of x to the fourth is going to be 0. The derivative of y cubed is going to be 3y squared. And now in the x squared y to the fifth term, the x squared is acting like the constant that's going to hang out. And the derivative of y to the fifth is going to be 5y to the fourth. Obviously, there's a little bit of simplifying we could do here, but we don't need to. So I'm going to leave it at that. Now, it's very, very broadly how partial derivatives work. They can get more complicated, but that's what you want to keep in mind. If you're differentiating with respect to x, everything else is considered a constant. If you're differentiating with respect to y, every other variable is considered a constant.